Okay, we're going to go ahead and get started, everybody. Thanks so much for joining us for our webinar, Using Optimus with Ricardo WAVE to get the best value from your simulations. We're going to be presenting an overview of coupling of Optimus and Ricardo WAVE. After my brief introduction here, we'll pass it over to the Ricardo folks to give you a 10-minute introduction of Ricardo WAVE. I'll then give you a short introduction of Optimus itself, and the bulk of the presentations will be done by a third person who will be describing two application cases. One, a performance versus emissions, kind of a classic trade-off scenario, and the second is a robust acoustic performance of a reverse flow muffler. The speakers that we have here today are Steve Rawnsley, who is the commercial manager for Ricardo Software. He'll be making the presentation about WAVE. He's based in Chicago. I'll be making the presentation about Optimus, the overview, and I'm based in Carmel, Indiana. And the application examples will be handled by Bram Vanderhagen, who's Optimus product manager. He's located in Leuven, Belgium, just outside of Brussels. The objectives of this webinar are first to give you a kind of a first order understanding of Ricardo WAVE and Noesis Optimus in case you're not familiar with one or both of these softwares. And of course the major objective is to introduce you to a new approach to leveraging both of these softwares, in fact any simulation software, by coupling with Optimus. And we hope that in the end, you'll have an interest to take this a little bit further. This WebEx, or this webinar I should say, is very one-sided with us doing the talking. What we'd like to invite you to is a more personalized WebEx or on-site visit where we can actually look at your situation and understand, or help you to understand, what the potential value is. I'm now going to pass it over to Steve, and he'll give you the WAVE overview.
Thank you, Mike. My name is Steve Rawnsley. I'm the commercial manager with Ricardo Software in the United States. Appreciate the opportunity to share a little about Ricardo and Ricardo Software's WAVE tools and its use with Optimus. Ricardo is a world-leading automotive and engineering technology company. We've been around the best part of 100 years, doing every kind of engine, whether it's marine, motorcycles, automotive, all the way through to the more recent land speed record in collaboration with JCB on their Diesel Max, and the very most recent McLaren supercar. We're based around the world, say established in 1915, about a couple of £100 million in revenue, one of the leading companies in this field. I'm in Chicago. This is where WAVE has been historically developed over the past 20 years. We also have teams in our Detroit office, of course, supporting the major automotive industry in the United States. Historically, we are based also in the United Kingdom, in Shoreham, and we have a large team in our Prague office, particularly doing support activities. And of course, we're expanding around the world as emerging markets such as China, India, taking a lot of engine development software. If there's one word that would sum up what Ricardo is, it's engines. Any type of engines from concept to production. As I mentioned, we're doing the volume manufacture of the McLaren supercar right now in our Shoreham office. We'll do any kind of project with you, whether you're looking at where the technology is going in the next 25 years, reducing emissions, particularly CO2 reduction, of course, is key for tax and price strategies around the world. Whether it's a turnkey project you want or just a small NVH study, we can apply our various tools to that. We do a lot of research in various types of alternate fuel vehicles, particularly E85 and boosted engines such as that. A lot of control work is done with Ricardo and Ricardo software products, and together with our other tools, we'll do research in twin vortex combustion, particularly for emissions reduction, as well as spray-guided gasoline combustion get the high efficiency gasoline engines equivalent to diesel technology. One of our more recent engines was an interesting study we did for our small Wolverine UAV engine, where WAVE and our other tools were used to do a small 3 horsepower heavy fuel engine for the US. Ricardo software, we are the key part of Ricardo developing these tools over many, many years. Most of the tools out there were general FEA or CFD tools, not specifically designed for powertrain. In-house, we have developed the tools specifically for engine and powertrain applications. Starting on the left side with FIRS, our FEA environmental workflow for the powertrain development, tying together all our mechanical tools such as engine for the crank train, specialist tools for the piston and ring development. And a big part of Ricardo's business is actually transmissions. We have our Sabre tool for shafts and bearings, and also Valdyne, what the name implies, developed initially for valve trains, but it's a general multi-body dynamics tool. What we're going to be focusing on today, though, is more on the fluid side. WAVE is one of the industry standard tools for engine performance, gas dynamics, and NVH. More recently, we developed a WAVE real-time module, taking the WAVE performance engine into the controls environment at an earlier stage in the production process. And for those of you that's doing combustion research in cylinder, Vectis is our in-cylinder automotive underhood 3D CFD code. We don't stand still with this. We've just recently launching a new product called Ignite, which is our vehicle performance and fuel economy complex systems tool, complementing the range we have. Focusing on WAVE, the bread and butter is engine performance. You're going to do your intake and exhaust manifold design, valve specification and timing, and of course recently most systems out there are boosted, not just the diesels but even gasoline engines these days. Combustion emissions, a big area. With WAVE you can look at trends in emissions and do more detailed in-cylinder emissions perhaps with Vectis. But a key area of use of WAVE, as we'll see in the next couple of slides, is acoustics, NVH for the intake and exhaust gas dynamics. We can couple these in a 1D, 3D simulation with Vectis. Typically you might be looking at detailed flow optimization of a catalyst flow or EGR mixing a manifold. Thermal analysis, everything's getting a little hotter, particularly on the boosted engines, so we want to make sure everything is still holding together well on the exhaust manifolds. You can take WAVE results, initial temperature out of your thermal analysis, and as I mentioned earlier, controls and transit analysis is a big part of developing your engines, and with WAVE and WAVE real time gives you a full suite of tools to do your controls development early in the process. Typical applications for engine performance, everyone knows you're designing your torque and power curves, and this is where tools such as Optimus comes in handy, because there's always a trade-off. More power, more torque, generally less fuel economy, so you always have this trade-off, and an optimization study with Optimus will certainly help here. What we're looking at here is a simple valve time-in, intake valve time-in variation of the fuel economy with the shaping the power and torque curves. There's a lot on this page. It really summarizes what Ricardo and Ricardo software can do for NVH gas dynamics on an engine. That's one of our key areas. WAVE is always used for the performance, but the advantage of WAVE is together with performance and NVH, you can couple the two together. It's all very well doing NVH and making a nice quiet engine, but if it just compromises your performance and back pressure, that's no good. So that's another excellent use of tools such as Optimus, where you can put a constraint in your back pressure targets over the entire exhaust system or individual components such as a muffler, and do the trade-off on meeting your sound pressure levels, the intake and or exhaust, and making sure you do meet those constraints on your back pressure targets. The tools we use is WaveBuild 3D, been developed over the last few years for creating muffler, typical intake exhaust component systems very, very quickly. The advantage is you can do an automatic meshing for the NVH analysis. This allows you to put it in the Optimus Workflow. So, for example, when our team have done 50 or 100 layouts, they may then do a little more optimization on baffle position, making sure the volumes are optimized, the number of perforations in a pipe, etc., to fine-tune the pressure targets so that the range of the engine performance. So again, that's something you can put in the Optimus WAVE workflow. So to summarize, WAVE, of course, is an integrated engine system solution for any kind of engine. It's been used over the past 20 or so years. It is a fast solver, and again, this is where the Optimus WAVE workflow comes in. You can run hundreds and hundreds of experiments very, very quickly. 1D gas dynamics, it's very, very fast to solve. Particularly if you're looking at MVH, you can put in automatic meshing of your mufflers, etc., the 3D geometry. And to be able to get the real turnaround, what you can do is use our run distribution license technique with WAVE. There's a couple of ways you can do it. You probably do in a large DOE with the Optimus environment. You can actually split all the individual experiments off onto a different CPU using our run distribution license. That's one way to really turn around these optimization studies very, very fast. Second is, perhaps less well known, as I think we're the only tool that does it with WAVE, you can actually run WAVE in parallel for a single job, such as a transient duty cycle, a couple of 100 seconds duty cycle. Instead of just using one CPU, typically you could run 2 to 4 CPUs to accelerate a single job for a long transient. So there's two ways of running, actually, with the same license technology. As I say, it's validated in numerous engine programs by Ricardo and our clients over many, many years. And, of course, we do couple mainly to our own internal CFD codes, but other industry standard codes out there, where there's mechanical control packages, MATLAB, Simulink, etc. And, of course, for customer-driven developments, world-class support throughout the world, and so on. So hopefully that's given you a bit of a background on Ricardo and Ricardo's software for anyone that may be new to us. And now I'll pass it back to Mike and the Optimus team to show you how this can be implemented in the Optimus world.
Okay, thanks, Steve. Let me now progress into the Optimus overview. Optimus, what we hope to show you with Optimus here is a new approach to derive greater value from your simulation-based design. And there are various ways that Optimus actually can help you to do that. One is by reducing wall clock time, getting more simulations done in kind of a critical one-day turnaround, simplifying your design work by allowing you to focus on the key parameters and also eliminating non-feasible designs right from the get-go, significantly reduce time needed to conduct high-fidelity 3D modeling. And this is something which will be much easier to explain when we show you, but essentially it's using meta-modeling or approximation models as well as direct optimization. Repeatable workflow, one of the things that Optimus will do for you is enable you to create what can be a very complex workflow, but it's completely repeatable. You can pull it up 6 months later and not have to try to remember where your files were and what you were doing. And finally, Optimus can enable you to improve reliability and robustness where probabilistic design parameters can be taken into account. So there are a number of different things that Optimus can do for you, and we're going to go through the various actual embedded techniques to show you how that's done. What I'm going to be talking about briefly is process integration, design of experiments, response surface modeling, single and multi-objective optimization, and robust design. Process integration, what do we mean by that? Process integration is the ability to link different software and automate their running. In this example up here, we see a relatively complex work process which consists of a number of different programs. You'll recognize some of these. You have a CAD package, for example. You've got finite element analysis, CFD, you've got post-processing. But what Optimus is doing is it's allowing you to automate all of these so that they're one continuous process that you can now kick off before you go home or before a weekend or whatever, and it will run the entire sequence automatically and also provide diagnostic information if you want sent to your cell phone. It also takes advantage of your IT infrastructure Typically, our users have intensive CPU-intensive software on HPCs and Linux clusters and other programs or local and so forth. So all of this is handled in this workflow. It does also, let me just add, enable you to put control into it using logic. So if step 1 gives you a bad result, do not progress to step 2 and so on. So this by itself can be a very powerful way of reducing your time or allowing you to do more runs of the software that you're running. Okay, the next aspect is design of experiments. DOE, and sorry, I went too many slides there. DOE has two very important purposes within Optimus. The first one is to allow you to identify very quickly the key design variables. In this problem that we're showing right here, on the right you see a picture. It's actually a 1D code used to model an injector valve, a diesel injector. And the design variables in this case are diameters. You have a blue and a red, as well as this angle or this half angle of the poppet or the valve itself. After running a design of experiments, in other words, a sampling of your design space, Optimus can extract out the correlations, the linear correlations between each of those design variables. And they're color-coded. It's very, very quick to understand how to use this. Basically, you have each of your design variables as well as the outputs listed here on the y-axis, and across the top, the x-axis, you have the same values, and you can now look at the relationship between each of these. So you'll notice that the first couple of these, as I go down from the top, there are what I call meaningful correlations between the inputs and the outputs. But by the time I get to this poppet half angle, which you recall is this valve angle right here, you'll notice that the correlation with the outputs is about 0, these deep blue blocks over here. And that's telling you that that particular variable is, the results are insensitive to that particular variable. And you can put your attention to other design variables or take it out of the equation completely. The other purpose for DOE is to enable you to build a interpolation model, or it has several different names: a meta model, surrogate model, approximation model, response surface. But what it is discrete bits of information that you got from your design of experiments. So for example, let's say you're looking at length, width, and height, and in your design of experiments you look at the minimum of each of these and the maximum of each of those. What the response surface is going to allow you to do is to determine what the in-between values are. So it's going to essentially interpolate between all of these and map a continuous surface. So now you have the ability of gaining information anywhere in your design space, and you can do it in less than a second running on a laptop. It's also portable, which means that the underlying simulation software that you use to get those various discrete points is no longer having to be run, and anybody can use this. So this is a very important part of the process typically, because from this you'll often do an optimization on that interpolated surface and extract out the optimal areas, which then you can go back into and do further refinement, experimental work, and so forth. So that takes us now to direct optimization. And to give you kind of a sense of what the software is doing for you, we have this truck body on the right here. We are trying to minimize the drag coefficient while maximizing the volume of this cab. They actually wanted to try to put a queen-size bed into this cab here. And of course, as you maximize the volume, you are going to get a conflicting objective in terms of the drag coefficient. So as I step through this, you'll see what the software is doing. On the left, we have drag, and on the x-axis, we have each run of the software, which in this case is a CFD software. initially, what Optimus does is it actually conducts a design of experiments just like you would. It, like you, has to understand how these different design parameters interact, and of course it's working on a highly mathematical basis rather than intuitive basis, so it's pulling out this information very directly. And then it hands off this DOE automatically to a optimization algorithm which progresses to further reduce the drag coefficient and find the best values. So that's just a very simple way of visualizing optimization. The software being able to help you by automating this and also by focusing only in the feasible and optimal zones. You notice that you're not getting a lot of sampling outside of the previous best design. At the high end of optimization, we have many of our automotive and aerospace users, for example, who use Optimus for robust design. Robust design is taking the optimization process a bit further. In this case, you have variability associated with those input parameters. For instance, you may have a build tolerance. So as a result of that variability, you're also going to get variability on your output. What Optimus is going to do is this. It's going to find the best result as it did in the previous example, but now it's going to look at the variation that results from the variability of your inputs. In this case, some of the results fall into a failure zone, and so you have a reliability issue. What Optimus then does is automatically finds a new optimum, which may not be quite as good as the previous one or the deterministic one, but one which ensures reliability. All the results are going to fall into the safe zone. And you also get a tighter range of results, which results in a more robust design. So the key here is mathematical efficiency. Statistically, this can be very long-running, and rather than rely on sort of brute force Monte Carlo sampling, there are some very clever techniques that allow you to do this in just a fraction of the number of runs and still get statistically significant data from that. So let me now just tell you a few things about the company itself. We've been releasing Optimus now we're actually going on 17 years. We're the largest OEM provider of embedded optimization, and what that means is we actually offer Optimus to third parties who have a push button type of single button click optimization, and that's important because we've had to put a lot of effort into the robustness and speed of these algorithms. We've got offices all across the world. I mentioned I'm in the Carmel, Indiana office. We've got offices in Europe, Japan, India, Israel, and so forth, as you would expect from a large installed base as we do. Our customers, of which we have over 2,000 now, include a substantial number of automotive companies as well as aerospace. But over the last 5 years, we've really broadened into just about every industry. Of course, anywhere you're doing simulation, you'll have the potential of taking advantage of Optimus. So that's my very brief introduction. At this point, I'm going to hand this over to Bram Vanderhagen, who will go through the examples. But let me just summarize some of the things that I've showed you here. I think you've gotten some hints into how this can reduce your total time or get more simulations done within a given time network, or excuse me, time frame. Simplify your design work by enabling you to focus on the key design variables. Through this meta modeling that I told you about, this interpolated response surface technique, you can get much faster results and then focus on the most optimal designs. You do end up with a repeatable workflow, and if necessary, you can put in the stochastic aspects, the probabilities. So, Bram, I'm going to pass the ball over to you now and bring this all to life here with the application examples.
Thank you, Mike and Steve, for the introduction. During the next 25 minutes of this webinar, I will present some application cases that demonstrate how this coupling between Optimus and Ricardo WAVE works. And the agenda for this part of the presentation is that we first go over a case study that explains a typical engine design problem where we have to make a trade-off between performance of the engine versus the emissions. After that first case study, I will show you an example of how a workflow is set up in Optimus, and I will also show you how you can wrap Optimus by some custom created applications. And in this case, I will demonstrate an Excel-based custom application. And then finally, I will conclude with a second case study that illustrates a design methodology for the robust acoustic performance of a muffler. So let's start with the first case, the performance versus emissions problem. The approach that we're going to follow during this application case is that we are first going to run a design of experiments in order to explore the complete design space. So we're going to run a large number of wave models simultaneously thanks to this coupling between Optimus parallel processing and also the wave distributed runs. After this DOE sampling and after looking at some post-processing plots, we will make a meta model of our simulations by creating an automatic best response surface. And for this, we are going to use the Clearview Analytics response surface model wizard. And at the end, we will do a multi-objective analysis in order to find a trade-off or a compromise solution between the engine torque and the fuel consumption. So let's start by explaining some details about the model. So this model is completely built in Ricardo WAVE build, and the model describes the complete setup of the engine, where we start with the intake lines and the airbox. Also, we have modeled the inlet manifold, where you can see the inlet manifold and also the 4 runners that connect the manifold to the cylinders. The cylinder head is also modeled in WAVE, and after the engine we have the exhaust lines that collect in the exhaust manifold, and we have the after treatment line where we have all the catalysts and first muffler, and at the end we have the second muffler, which will do the acoustic silencing. So this model actually represents a 4-cylinder gasoline engine with a spark ignition. And in order to make it more realistic, we are not just going to run the model for a specific operating condition or for a specific engine speed. Instead, we are going to make a sweep over the complete RPM range, going from 1000, which is engine idling, all the way up to 8000 RPM. And each of these 8 cases are set up in the case constants inside Ricardo WAVE. So for the optimization, we are going to identify a couple of parameters that can be varied by the parametric optimizer. And for this example, we have chosen to vary the angle where the intake valve has maximal lift. So that's actually expressed in degrees of the crank angle, and that's shown in green on the top right plot. Also, the duration of the intake phase can be varied. So these are two parameters that are related to the valve train. A third parameter is more like a geometrical parameter, and in this case we have chosen to also vary the dimensions of the, or more specific, the length of the runner at the intake. So that's actually this length that we can change. As a result of our calculation, we are interested in three quantities. First of all, the brake-specific fuel consumption, which is expressed in SI units. Also, we are going to look at the volumetric efficiency, which indicates how well the cylinder is filled. And in order to have an idea about the performance, we are going to look at the torque expressed in Newton meters of the engine. So like I said, we will optimize this engine for a complete RPM range between 1000 and 8000 RPMs. So we will make three objective functions where each objective function is just a weighted summation of the BSF SI, the volumetric efficiency, and the torque SI at 1000 all the way up to 8000 RPM. So after the definition of our optimization problem, we are going to prepare the model in WAVE, and this model is prepared in three different WAVE files. First of all, we have the WVM file, which is a WAVE model input file. This is basically just an ASCII file, so a text file where you can see everything that is inside that file. The results of the calculation are stored in two different results files. First of all, we have the text-based sum file, which contains all the cycle averaged values. And this is actually a very important file for this kind of design of experiments and optimization. And there is also a binary file with the WVD extension, which contains all kinds of time-dependent data. And this file is less useful for this kind of optimization, but it might be useful in the later states if we want to do some acoustic analysis. And this is something that will be demonstrated in the second case study. So in Optimus, setting up a project where Ricardo WAVE is integrated is actually very simple, because we have dedicated file parsers for each of these Ricardo WAVE files, and basically they just require you to select the model file or the input file, and after an automatic parsing, Optimus will show you all the values that are available in that file that can be used for optimization. And as a user, I just have to pick and select the variables that I'm interested in and add them to my Optimus project. The same works for the definition of the outputs. So we have file parsers for both the sum files and for the WVD files. And you just have to load the file, pick the variable, and select them as optimization variables. And how this works exactly, I will show in a live demonstration after this case study. So the resulting workflow looks like this. It literally takes less than 5 minutes to set this up. And once this workflow is set up, the following principle will occur. So every time Optimus will propose a new design, it is substituting new numerical values for my input parameters in the WVM file. This modified WVM file is then used by the WAVE solver, which is running in a batch mode. And at the end, the sum file and the WVD files are produced. And in this case, from the sum file, I will extract my fuel consumption results, my torque results, and my volumetric efficiency results. Running one time this entire workflow takes about 1 minute. And in this 1 minute, WAVE is running each of the 8 different cases. And thanks to the integration of WAVE distributed runs with Optimus Parallel, you can actually run multiple experiments simultaneously on multiple CPUs. So once we have a running workflow, we can start doing some useful things with it. And in this case, we are first going to do a design space exploration. And to do that, we have chosen to run a Latin hypercube design of experiments. This means we are going to run our WAVE model 100 times. And based on these 100 different designs, we can extract some information about relations between input and output parameters, and also between outputs and other outputs. What we can see from this correlation values plot is that if we look at the influence of the runner length on the fuel consumption, we see that there is a positive correlation. That means if we make the length of the runner longer, our fuel consumption will increase. What we also see is that there is a not so clear relation, or a not minor influence of the angle for maximum intake lift on the 3 defined results. There is also a clear negative correlation between the duration of the intake phase and the torque and the volumetric efficiency. So if we make the intake phase longer, our torque and efficiency will go down. And this will have something to do with the valve overlap. Another relation that we can clearly see here is that if our efficiency increases, also the torque of the engine will increase. If we take a closer look at the influence of the duration of the intake phase on the torque and the efficiency, and also on the fuel consumption, we see that there is a significant change in behavior that happens around 5,000 RPM. You see, for example, here that below 5,000 RPM, if we make the intake phase longer, the torque and the efficiency will go down, but suddenly above 5,000 RPM, we see that making the intake phase longer will actually increase the torque and the efficiency. The exact opposite will happen for the fuel consumption. So below 5,000 RPM, making the intake phase longer will increase the fuel consumption, but above 5,000 RPM it will decrease the fuel consumption. So after this initial design of experiments, we have done 100 discrete runs of the WAVE model. And what we want to do now is we want to fit a response surface model or a mathematical representation through these points in order to have a continuous model. And therefore we use a response surface modeling wizard, which will try a whole set of different response surface modeling techniques on the data set, and it will automatically, for every output, generate the best model based on some cross-validation and some other statistical tests. And the model we will get at the end of this toolbox run will be the best model for that specific output. So what we have now is a continuous meta model of the fuel consumption and of the engine performance and the volumetric efficiency as a function of all the input parameters. And as you can see, the toolbox proposes different response surface models for the different outputs, like for example feed-forward neural networks and support vector machines. Once we have such a response surface model, And once we have a good quality, we can start actually optimizing this. So what we can do is we can either do a direct optimization, where we evaluate the model results directly with the wave simulations, or we can use the meta model or the response surface model to predict the engine performance and the fuel consumption. And in this case, we are going to use a second approach where we use the meta model, and we can either optimize the engine for maximal torque and maximal volumetric efficiency, or minimal fuel consumption. But as you can already expect, these are two conflicting objectives, so we will have to find a Pareto optimal solution by applying a genetic non-dominated sorting algorithm. And the result is that we get such a Pareto trade-off curve, where we of course want to attain this utopia point, which represents a design with a very high torque but also with a very low fuel consumption. Of course, taking into account the physical reality, we cannot attain this point, so we have to either choose a point where the torque is low but also with a low fuel consumption, or a point where the torque is very high but unfortunately with a high fuel consumption. When we have such a Pareto curve, it's very easy to make a trade-off where we, for example, choose a possible compromise solution here, which is only a small reduction in torque, but a much larger reduction in fuel consumption. And this can be our trade-off point for the engine. So, to conclude, this application case indicated that it's very easy to tune the engine for either maximal performance or best fuel consumption, or to choose a trade-off between these two conflicting objectives. We can also, for example, limit the fuel consumption by putting a high constraint, and then find the optimal or the highest torque that the engine can produce. So this brings me to the second part of my presentation, where I want to give a quick Optimus demonstration and also give an example of an Excel-based custom application that is driving the optimizations in WAVE. Therefore, I will quickly switch to Optimus, and here you see the Optimus main screen, where you can drag and drop the WAVE components in the workflow. For example, here we have the file parser for the WVM file. We also have a file parser for the sum file. And by editing both of these icons, you can, like I said, you can just load up the WAVE model file. It will parse the file, and it will show you all the possible parameters in the file. For example, let's suppose I want to modify the runner length. I select it here, I add it to my Optimus parameters, and that's the parameterization of the input. For the sum file with results, I can do exactly the same. After the file is parsed, I can just look for, let's say, the torque values. In this case, I will take the torque value at 5000 RPM. I add it to my Optimus workflow, and I close this dialog. The only thing I still have to add now is my WAVE solver, and I connect my input file to the solver, and I connect the solver to my results file. And after the connection is made, I have a fully functioning integrated WAVE project inside Optimus. And this project can now be used to run optimizations and run design space explorations, which I've already done here. Let's say, once you have run a design of experiments, you can post-process this data with different post-processing plots that will give you all kinds of valuable information about your correlations and about the relations between your design parameters, like what you can see here, for example, on this bubble plot. So this is a very short demonstration of Optimus. Let's switch back to the presentation, where I'll just say a few words about a custom application we've built for a customer that wanted the entire organization to utilize Optimus in combination with Ricardo WAVE, but without exposing the users to Optimus. So therefore, Optimus can be fully wrapped by a custom application. In this case, that was Microsoft Excel, where we have created a dashboard where the user can set up the complete optimization project. He can do all kinds of design space exploration and optimization, set up the workflow, choose the inputs and choose the outputs, all from within an Excel graphical user interface. And how this works is demonstrated on this slide here, where you can see that the user can select the kind of design space exploration or optimization. In this case, he just wants to run a table method for 5 different designs of the wave model. He can select the corresponding input parameter values. And once this is done, he can click on a button, Run. That will run the complete optimization. In fact, it will create the Optimus project first. It will run the wave model for the different designs, and it will bring back the results inside Excel, and Excel can then be used for further report generation and post-processing. In this case, users can save a lot of valuable simulation time because the problem setup is the same. But when you want to run design space exploration or an optimization, it's all going much quicker than manually parameterizing the wave models and running the simulations manually. So in this case, we had an 85% reduction in user time. So let's go over to the final application case, which outlines a design methodology for a robust acoustic performance of a reverse flow muffler. In this case, we are not just going to run Ricardo WAVE, but we have 3 different Ricardo tools that are running in an automated workflow. And we're going to look at some more advanced post-processing that will give us some interesting insight in the model behavior. And at the end, it will lead us to find a reliable and robust optimum that will prevent undesired behavior. So the model that we're going to use is introduced here. It's a simple reverse flow muffler that has an inlet pipe, a reversal or a middle pipe, and an exhaust pipe. The muffler is subdivided in 3 different cavities, divided by these 2 baffles here, and the inlet pipe and the reversal pipe have some perforations in it. So what we want to obtain in the end is to have a muffler with a minimal sound pressure level at the exhaust, while making sure that the back pressure that the muffler puts on the engine is not too high. So the inputs for this optimization problem are the following. So we can change the vertical positions of these baffles. We can also change the diameters of the holes in the middle and in the inlet pipe. And depending on the diameter of the perforations, we can punch more or less holes in the muffler. So this will be a depending optimization problem, and thanks to Optimus conditional workflows, it is very easy to deal with these. The outputs for the model are the back pressure curves as a function of the engine RPM, and also the SPL curve, or the sound pressure level curve. Of course, this we want to minimize. while we want to make sure that our back pressure is not exceeding a constraint. So we use 3 different Ricardo tools. First of all, Ricardo WAVE Build 3D. We have then Ricardo WAVE for the solving, and we use WAVE Post for the post-processing and to generate these SPL curves. The simulation procedure starts by modifying the 3D wave geometry and remeshing the model. This model will be solved with the WAVE Acoustic Solver, and afterwards WAVE Post will be used to post-process the results and to create the SPL and back pressure curves. This translates in the following Optimus workflow, where we have as input parameters the hole diameter and the baffle positions. Depending on the hole diameter that Optimus proposes, a conditional workflow will be launched, and depending on this hole diameter, Optimus is going to propose a number of holes that can be punched in the pipe. So depending on this value, one of these 3 branches will be run, and the simulations can be extracted from the results files. So in our design of experiments, we are going to do a max-min DOE, which is a uniform design space sampling where 2 points are located in such a way that they are not too close to each other in order to maximize the minimal distance between them. And this will result in a very homogeneous sampling. And after this max-min DOE, we can decide which perforation diameter we could choose. From this plot here is showing the SPL as a function of the hole count. We could see that holes with a diameter of 4 mm are shown in green. The ones with a diameter of 8 mm are shown in yellow, and the ones with 12 mm are shown in red. And from this we can conclude that there is a negative linear relation between the number of holes and the SPL. Also, for each hole diameter, the lowest SPL is obtained for the highest number of holes, and the same improvement is found for each of the 3 different hole diameters. So we can just take any arbitrary diameter, and in this case I had chosen 8 mm. And for 8 mm you can see that the more holes we have, the lower the SPL values. So in this case 140 holes gives much better sound pressure levels than just 20 holes. If we look at self-organizing maps, which is some kind of fingerprint of our data, we could see that the region where we have the lowest sound pressure level corresponds with a region where our back pressure is consistently exceeding the 1.165 bar, which is our maximal constraint. So this will lead us to a boundary optimum, and this can eventually give problems with the robustness and the reliability. So what we do here is we do an efficient global optimization where we want to find the real optimum with as few experiments as possible. And instead of doing a manual design of experiments, creating a manual response surface and do the optimization on a fixed response surface, we will now use a sequential or an adaptive approach where we enrich the response surface with points in regions where we find it interesting, where we can expect the most improvement of our model. So this plot represents the progress of our optimization, where you can see that we have a monotone convergence. Our objective was to minimize the sound pressure levels, and you can see that they are going down monotonically. But there is some oscillations in the maximum back pressure. So initially we are above the constraint. We find a region with low back pressures, but then suddenly if we find lower values for the SPL, the back pressure will go up again until it reaches the constraint at the end. So this will be a boundary optimum, and that can give problems with the reliability. So if we look here at the parallel coordinates plot, we can in fact find two optimal solutions that have similar results for the sound pressure level, but one has a better or a higher safety margin with respect to the constraint. So this blue curve is in fact having a similar SPL as the red one, but the back pressure is lower. Thus, the design is better. So by comparing this, we see that it is confirmed by the numerical details. The SPLs are the same, but with a slightly lower back pressure. So at the end, we can compare our initial design in red with our final design, which is the one in blue here, and we can see that the SPL levels have indeed gone down with a decrease of the back pressure. So to conclude this case, the optimal point that the optimization algorithm found had a very good acoustic performance, but it was located on the boundaries of our constraints. So this is not safe in terms of reliability and robustness, and the slightest deviation in input parameters can result in failure of our design, being it out of constraints. And by looking at this post-processing plots, we have found that actually our second best solution had a similar acoustic performance, but a larger safety margin with respect to the back pressure. So there is less engine restriction for the same acoustic performance. So this part of the presentation has indicated that it is very easy to integrate Ricardo WAVE with Optimus, thanks to these direct interfaces. And in the first case, we have seen a trade-off analysis where we make a trade-off between performance and fuel consumption. And in the second case, we were able to avoid product failure by choosing a robust and reliable optimum. Overall, with the coupling of Ricardo WAVE and Optimus, you can first of all save time by driving WAVE combined with other tools in automating repetitive tasks. We can also improve the performance of your designs by these automatic parametric studies and by applying intelligent optimization methods. And we can consolidate knowledge by first of all creating fast and accurate meta models, but also to make optimization accessible for a larger audience by sharing your optimization workflows through custom applications like Excel, etc. So this brings me to the end of my part of the presentation. I will now pass the word back to Mike, and it is now time for some question and answers.
Okay, thanks very much, Bram, for that. That now takes us to the last section, the Q&A, and some of you have already texted in through the chat box some questions, and we've answered some of those, and I've gotten a number of them in front of me here that we'll go through as time permits. Since some of you will be hanging up here before we're done, let me just once again invite anybody who's interested in taking a closer look. We would be more than delighted to do a WebEx with you on a one-on-one basis, talk about the specific software that you're doing and looking at your processes, try to identify where and how much value Optimus can provide. Okay, well, let me go ahead and get started here. This is a question that we often get. What other codes can Optimus be coupled with? And I'll go ahead and answer that one. Optimus is actually a very generic type of package. It's designed to work with virtually any simulation or mathematical modeling package. Probably 95% of all the packages out there. CAD, acoustics, CFD, finite element analysis, crash, kinetics, so forth, as well as Excel, MATLAB, and those type programs. It also works with in-house codes, provided you have an ASCII input-output format that we can read or address, as well as a command line batch mode to kick off the process. Next question. Can you talk a little bit about parallel processing in more detail? And I think what this gentleman or person is referring to is how do we take advantage of parallel architectures and what's available. So I'm going to pass that over to Brown.
Yeah, Optimus can definitely do parallel processing. There are direct couplings between Optimus and many of the widely used cluster systems, like for example PBS or LSF. And Optimus also makes the most efficient use of your multi-CPU or multi-core machine. So if you have enough licenses available, Optimus will make sure that it starts multiple instances of the solver at the same time in order to run multiple experiments, multiple simulations in parallel in order to cut your overall simulation time in half or in a quarter or so on, depending on the number of runs that you do in parallel.
Okay, let me proceed here with another question. Can you target both exhaust back pressure and acoustic SPL levels in the same workflow?
Yes, absolutely. That's one of the key strengths of WAVE, and particularly using it within the Optimus environment. You can put exhaust back pressure over the entire system, or just an individual component as a constraint, and run WAVE at the same time to get the NVH sound pressure levels out. So that's certainly one of the advantages of the tools such as WAVE that does engine performance and NVH coupled together, not just one or the other.
All right, we've used up all of our available time here, so we're going to go ahead and close this webinar. Thank you very much for attending. I hope you found this interesting and potentially useful. And as I mentioned before, we invite you to a one-on-one type of a scenario where we can look more closely at your situation. If we did not get to your questions, we will answer them via email. And of course, you can get more information about WAVE or Optimus on the websites, or you can respond back to the invitation letter itself if you have any additional questions. Please stay tuned. We do offer webinars throughout the year on various subjects, and you can go to our website to get a listing of those. So thanks again for joining with us, and at this point, I bid you goodbye.